Hello and welcome to Lecture 6 for Unit 3 of Intro to Logic. We're going through derivations and predicate logic. Last time we talked about universal out and existential in. So universal out is a way of using a universal statement. Existential in is a way of getting an existential statement. So we need two more things. We need a way of using an existential statement and a way of getting a universal statement. That's what we're going to talk about today. So first, we're going to talk about a way of using an existential statement, that is, using a statement whose main operator is the backward z. So that's called existential out. So let's look at this example here. Suppose we know something lives on Venus. If we know something lives on Venus, we can't assume that it's any particular person we know something else about. We can't assume that it's the same person who we know did something else or other, right? All we know is that something lives on Venus. We don't know what that something is. So unlike universal out, we can't just take the universal statement, apply it to any name we want. We've got to apply it to a name that we custom make just for the purpose of naming the thing that lives on Venus. So what we're going to do is we're going to make up a new name. So the way existential out works, you start with an existential statement. Let's look at the informal version. Backwards EX, something about X. We're going to replace the X, drop out the quantifier, the backwards EX, replace the X with a new name. So a new name is a name that doesn't already occur anywhere in the derivation. So it's not a name you're already using. You're making up a name. It's like saying something lives on Venus. Let's decide to call that something Alf. Therefore, Alf lives on Venus, right? You're making up the name as a new name, not as a name that's already in use. So if we're already using the letter A or B, we've got to use the letter C. It's got to be a name we're not already using in the statement. So let's try a derivation that uses existential out. So let's try this number here, this derivation here. First premise, all F's are G's. Second premise, something is F. We're going to show that something is G. And this is still a direct derivation. So we're going to start with the existential out. So we're going to start with line 2. So line 2 says something is F. We got to give that something a name. We can give it the name A, but we're only allowed to give it the name A because there are no A's anywhere on the lines. Even the show lines, you're not allowed to use a name that occurs on the show line or a regular line. But there's no A's in lines 1, 2, or 3. So we can use the name A for the thing that's F. So we're taking off the backwards EX on 2, replacing the X with a new name. So we can use A. So that's 2 existential out. Now, universal out, we have the upside down A, doesn't have the same restriction. So we can do universal out on 1, and we can make the X in 1 into an A. So if every X, it's true that FA arrow GA, FX arrow GX, and it's true of A that FA arrow GA. So that comes from line 1, universal out. Universal out doesn't have that restriction. You can use a name you're already using. Now we can do modus ponens on 4 and 5. We get GA. And then because A is G, something is G. So we get that something is G, backwards EX, GX, by existential in on 6. And that's our derivation. Very good. So what we do is we take off the backwards EX, or EY or EZ, whatever the variable is, replace that variable with a new name. So it'll be important in this next one that we use a name we're not already using, because this one's a little complicated. So the premise says if something is F, then for every value of X, if it's not F, then it's not G. There is something, it's not F and not RAX. We're going to show that if FB, then there is an X, not GX. So whenever you're trying to show a conditional, you're going to show it by conditional derivation. So we can do a conditional derivation here. We're going to assume FB. And we're going to show the then part of our original show line. Show there is an X, not GX. And we'll do that by direct derivation. All right. So look at line 1. The main operator of line 1 is the arrow. So we can't do existential out on 1. But we can do existential out on 2, because in 2, the backwards EX is the main operator. So we got to take off the backwards EX, replace the X everywhere in the statement with a new name. Now, we're already using the letter A at line 2. We're already using the letter B at line 4, line 3 and 4. So I have to replace the x in 2 with a c. And replace both the x's with the same name. It has to be a new name, so we're using c. That's 2 existential out. Now, if I want to use line 1, I can't do existential out on 1, but what I can do is I can do modus ponens if I get that something is f. Well, I have that b is f, so I get that something is f from that. B is f, therefore something is f, so that's 4 existential in. Now I have the if part of 1, so I get for all x, if not fx, then not gx. So that's 1 and 7, arrow out. Now I can break up line 6. I've already dealt with lines 1 and 2. I can break up line 6 into its 2 parts. The only part I need is the not fc though, so I'm just going to get that. You see that that's going to give me what I need for 8. I don't need the second part of 6. So line 8 is universal out. So universal out, you can use a name you're already using. So I'm going to use C. So I have not fc. That's going to give me something I can use. Now I can do modus ponens on 9 and 10. Get not gc. Then I have that something is not g because c is not g. So I get there is an x, not gx. That's existential in on 12. So we did existential out only once in this problem at line 6, but we used a name we weren't already using. So now we've shown what we need to show, and we're done. All right. Oops, didn't mean to do that. Let's do this one from scratch. Let's not look at the answer. All right, so we've got everything is f if and only if it's g. All and only f's are g's. Everything is not f. Show that it's not true that something is g. So here we're trying to show a negation. Since we're trying to show a negation, let's do it by indirect derivation. Let's assume that something is g. Use show line to show splat. We always show splat for indirect derivations as our next, and we show splat itself by direct derivation. So we're doing an indirect derivation. You assume the opposite of what you're trying to show, then you try to show a contradiction. This contradiction itself we represent with splat, and we show it by direct derivation. So now we have 3 lines to work with, 1, 2, and 4. And one thing I should have emphasized already, is that when you're doing existential out and universal out, you want to do existential outs first. You want to do existential out before universal out. So if I do the existential out first here, and I get GA, then when I go and do the universal outs on 1 and 2, I can use the A again. If I did the universal outs first and I got FA double arrow GA and not FA before I did the existential out on 4, when I went to do the existential out, I couldn't use A because I had A on earlier lines. It wouldn't be a new name, and then they wouldn't match. So this is a very important rule of thumb. Do existential outs first and then do universal outs. So I did the existential out on 4 first. Now I'll do the universal outs on 1 and 2. Okay. Now I need to do something with line 7. The one-way arrow changes to the two-way arrow changes to a one-way arrow. Now I wanted to go from GA to FA because I have GA, and if I got FA, I'd get a contradiction. So I wanted to go in that direction. So I got FA from 6 and 9. You could also do the modus tollens here, but I'm doing the modus ponens. So now the FA and the non-FA contradict each other. 8 and 10 splat in gives me splat. I've shown splat, and I've shown that by indirect derivation. All right? Good. That's the same derivation. All right, so that's it for existential out. It's the same as universal out, except you have to use a new name. You can't use a name you're already using. That's pretty much all there is to know about existential out. So we have existential out and existential in. We have universal out. We don't have universal in. In fact, there is no rule of universal in. If you want to prove a universal statement, you've got to use something called universal derivation. So this is a new proof technique. Just like there's no conditional in, arrow in, there's only an arrow out rule. Instead of arrow in, we have conditional derivation. That's a way of proving a conditional statement. We're going to have a way of proving a universal statement. How do you prove that a certain formula holds of everything? How do you prove that something is true of everything? It's not enough to prove that it's true of A. It could be true of A and not true of anything else. It's not enough just to prove that it's true of B. It could be true of B and not everything else. What we need is a method of proving that if we can prove it for one thing, we can prove it for everything else as well. Right? How do you do that? Well, what you do is you need to make up a new name. Suppose I make up the name Frabjous, and I can prove that something is true about Frabjous. Now, since I just made up the name Frabjous, I couldn't have any prior information about Frabjous. I just made that name up. Couldn't have any information in my premises about Frabjous, because that's a new name. But if I can prove that something is true about Frabjous, it couldn't be anything special about Frabjous that makes it true, right? Therefore, it's got to be true of everything else as well. So the way you do a universal derivation is in order to prove the universal statement, there's no assumption, you just put in a new show line to show the same statement with a new name n, right? You take out the quantifier, you replace the variable with a new name. If I can show that, then I've shown the universal statement as well. So I'm going to skip this because I'm going to walk you through the process anyway. So let's see how this works with this particular derivation here. First premise is all f's are g's. Second premise is everything is f. Show that everything is both f and g, right? So if the show line's main operator is the epsilon a, that's the only time you're allowed to use universal derivation. So here the show line's main operator is the epsilon a. So over in this box here, I'm going to write UD for universal derivation. So in addition to CD, ID, and DD, we now have another kind of derivation, UD. And the way UD works, it's kind of like indirect derivation and conditional derivation. You get a new show line, but unlike them, there's no assumption. There's just a new show line. So I'm going to put a new show line. What you're going to show is something just like the universal statement, except you take out the quantifier and you replace the variable with a new name. Now there's no A's in lines 1, 2, or 3. Since there are no A's in lines 1, 2, and 3, the letter A is new. So I take off the for all x, I replace the x's with A's. That's what I need to show. And I can show that however I want. I'll show it by direct derivation. So now I can use lines 1 and 2 to try to get FA and GA. Well, I can change both the x's in 1 and 2 to A's. So universal out on 1, universal out on 2, sorry, it's FA. Now I have what I need to do modus ponens on 5 and 6. I get GA. Then I can put 6 and 7 together to get FA and GA. Notice that I'm always working on the most recent show line. So I'm trying to show FA and GA. So I can just put FA and GA together. 6 and 7, ampersand in. So I've shown FA and GA by direct derivation. And the way universal derivation works, just like conditional derivation and indirect derivation, you don't need to get the exact thing on the show line. You need to get the next show line. So if I get FA and GA, where FA, where the A is a new name, and the statement I'm showing is just like the universal statement, except with the new name in place of the variable, then I've shown this by universal derivation. So universal derivation, if you cross off the show line below, you can cross off the show line for the universal. So that's all there is to this derivation. All right. So let's do another one. First premise says, if anything is G, then nothing is F. FA and not an HB. Show that everything is not G. So again, we're going to do this by universal derivation. The main operator is the epsilon A in our show line. The main operator of the show line is the epsilon A. Do it by universal derivation. There's no assumption. There's just a new show line where we have to show an instance of the universal statement with a new name. Now, A and B already occur in line 2. So I'm going to use C instead. I'm going to show not GC. Okay. Now here we can show this however we want. We can do either by direct or by indirect. Guess I'll do it by direct. Now I can do universal out on 1. I get GC, right? I want to make that a C because I do most tolons on this. It'll give me the not GC. All I do is change the x's. I leave the y's alone. Now that says if C is G, then nothing is F. But I know that A is F. I get that from line 2 by breaking up line 2. If A is F, then something is F. There is a y, Fy, existential in on 6. If I double negate that, I'll have the negation of the right side of 5. So now I can do most tolons on 5, and I get not GC. 5 and 8. Arrow out. That gives me not GC, and therefore I've shown this by universal derivation. So all you have to do is get the show line below it for universal derivation, and you can cross off that show line as well. I'm not sure why this is taking so long. There it goes. All right, so let's do, happens a lot because you know when you do translations, the upside down A usually goes with an arrow on the inside. Happens a lot that you'll want to do a conditional derivation within the universal derivation. So let's see how that happens in this problem. All F's are not H. Everything is either G or H. Show that all F's are G's. We'll do this by universal derivation. Because the main operator of the show line is a universal. So, sorry, we just need a new show line for universal derivation where we show an instance. I can use A, so there are no A's in lines 1, 2, and 3. So I'll show FA arrow GA. Now that's a conditional, so I want to show that by conditional derivation. I'll assume FA, new show line to show GA. And finally, GA I'll show by direct derivation. So now I go back to lines 1 and 2, but I can do my universal out. I get if FA, then not HA. Right, these are universals, so I can use letters I'm already using, GA or HA. I can do modus ponens from 5 and 7, get not HA. Then I can do wedge out on 8 and 9, right? Either GA or HA, but not HA, so I get GA. That's what I was trying to show, so I can cross off that show line. And with conditional derivation, if you cross off the show line below it, you can cross off this one as well. And the same is true of universal derivation, so I can cross off the show line at line 3. Good. All right. So this next one's pretty complicated. In this one, we're going to do a universal derivation the other way around. We do a universal within a conditional, right? And premises say all F's respect A. For everything, if there's something that respects A, it's happy. Show that if something is both F and G, then everything is happy. So notice in this one, the universal is not the main operator. The universal occurs after the arrow. The arrow is the main operator. So in this one, we're going to start with a conditional derivation. We're going to assume that there is something that's both F and G. And show for all x, hx. Oops. Show the then part of the original show line. Now we have a new show line. This show line, now the main operator is the upside down A. So we'll show this show line by universal derivation. Yep. Universal derivation, there's just a new show line. Right? Now we're already using A at line 1 and 2, so we can't use A. We're going to show HB. And we'll show that by direct derivation. Okay. So now, remember you want to do existential outs before universal outs? There's an existential at line 4. We're going to do existential out on 4. When you do existential out, you got to use a new name. So I'm going to use C. So I'm already using A and B. So I take out the backwards ex on 4, I replace those x's with a new name. Now I'll do my universal outs on 1 and 2. Now what does it make sense to change the letters in 1 and 2 to? Well, we have FC, or we're going to get FC very quickly, so we want to change the x in 1 to a C. And we're trying to get HB, so it makes sense to change the x in 2 to a B. All right. Now to use 8, I need FC, so I'm going to take FC out of 7. Then I get RCA, right, from 8 and 10, modus ponens. Well, if C respects A, then there is a Y that respects A. That's existential in on 11. That gives me the if part of 9, so then I get HB from 9 and 12 modus ponens. So now I've shown HB. The way universal derivation works, if you cross off the show line below it, you can cross off that show line. And the way conditional derivation works, if you cross off the show line below it, you can cross off that show line. Very good. All right, so this one we're going to do an indirect derivation within a universal derivation. So we're trying to show that everything is f. To show that everything is f, we're going to show an arbitrary new name is f. So we'll do this by universal derivation. We get a new show line. We'll show FA. We can use A because we know A is in lines 1, 2, and 3. Rather than doing this by direct derivation, we'll do it by indirect derivation. So indirect derivation, we're trying to show FA. We're going to assume not FA. Then show a contradiction. Show splat. All right. So from line 1, we get FA double arrow not GA. 1 universal out. Make 1 about A. Now the two-way arrow will change to a one-way arrow in either direction. Now we're not doing modus tollens on this version, not FA arrow not GA arrow FA, right? Because we don't have FA, we have not FA. So we want the FA on the right so we can do modus tollens. So 7 double arrow out. We can do modus tollens now with 5 and 8. We get not GA. The modus tollens always gives you the negation of the if part. So if it's already a negation, you get a double negation. So 5 and 8, 5 and 8, arrow out. Modus tollens form of arrow out gives us not GA. I can take off those double negatives, get GA. Now 2 says nothing is G, but we just got that there is an X, GX. What did I do there? It's 9 double negation, kind of drawn. And then this is existential in on 10. Now we have a contradiction between line 2. So see line 2, doesn't want to stay in frame. 2 and 11 splat in. So now we've shown our contradiction, we've shown FA, we've shown that everything is F. Very good. So we'll do one more here. This one will make it even more complicated. We'll do a conditional derivation, then inside it we'll do a universal derivation, and inside it do an indirect derivation, right? So why would you know to do that? Well, let's look at the premises. For all x, fx arrow, everything is h. It's not true that there is something that's both h and g. Show that if something is f, then everything is not g. Okay. Now the main operator here is the arrow. When the main operator is the arrow, you want to do it by conditional derivation. We're going to assume that something is f, put in a new show line to show that everything is not g. Now the main operator of this new show line is universal, so we're going to do it by universal derivation. We just get a new show line, we can show not GA, because there are no A's up there. And then this is a negation, so I'll do it by indirect derivation. Assume that A is G. show that leads to a contradiction. Show that leads to splat. Now, splat you always show by direct derivation. All right. So existential outs before universal outs. So before I deal with line 1, I'm going to deal with line 4. So FB, I have to use a new name when you do existential out. Now I can't do existential out on 2 because the main operator is the negation, right? So what I'm going to do with 2 is I'm going to try to get the opposite of it for my contradiction. I'm not going to try to deal anything with 2 yet. Would be nice if we had a negation rule, but we haven't learned those yet. So we're nothing we can do with 2 other than get a contradiction with it. We can do something with line 1. Now we can do universal out on 1. We get FB arrow for all y, hy. Now I made it a B because I had FB, and I wanted to match what I have. Now I have what I need to do most ponens for 9 and 10. I get everything as H. Sorry, that's arrow out for most ponens. Now what do I want to do? Well, I have GA. If I could get HA, I'd have HA and GA, and that would give me what I need to get a contradiction with 2. So I'm going to change, I'm going to do for all y. I can change that, that's universal. I can change the for all y and 11 to anything I want. But I'm going to change it to A, because that'll give me HA and GA. (7) and 12, ampersand in, I'm sorry, that's ampersand in. Now from that I get there is an x, HX and GX. Right, 13 existential n. Now I have a contradiction between lines 14 and 2, right? Notice that 14 is the opposite of 2. So I've shown contradiction, I've shown this, I've shown this, and I've shown this. Right? So that's all there is for today's lecture. You're ready to do exercises 8C and 8D. See you in the next one.